Hi, today I'm going to show you how to use the averaging of all data when you want to do seasonal decomposition. This would be equivalent to a process that's in POMQM, a multiplicative decomposition process. And later in this session, I will tell you exactly what model in POM must be chosen in order to replicate this information that I have here. For now, let's go ahead and consider this time series. This is a 5-year time series. It shows organ sales for a music company or music store. We have 5 years of data. We have quarters 1, 2, 3, and 4. So if you were to think of this as a time series, quarter 1 of year 1 would be time period 1. Then this would be time period 2, time period 3, time period 4. These are past data values. And then time period 5, 6, 7, 8. So that you would write the time series in this fashion if you were to write it in a column. Now, we're going to need to work with this. Let's go ahead and show you a graph of this time series. Here's a graph of the time series. You will see the seasonal variation in the data as you move, and you can also see that there is trend within the data. So we need to work or use a model that accounts for both seasonality in the data, which is repetitive and recurring every year, and we also need to account for that gradual upward trend in the data. Now, the method that I'm showing, your book says that if you're going to, if you have trend and seasonality within the data, to use the centered moving average method, the CMA. But that's a little tedious because of all the moving average that you have to do throughout the process. So instead of that, I'm showing you this, which is the average of all data. This is how it works. Notice how I have designed the data so that all the quarter ones or all the season ones are listed together in a column. What we need to do is to total the data for each season. So if I were to total this column, I get 50, I get 28 here, 30, and 92. The year totals for every year are listed in this column total right here at the end. If I were to add this up, I get 200, which is essentially the summation of all of the data. Here's my time series. I'm going to block it out over here for you. So the 200 is the summation of all of this 20 period time series. 5 years times 4 quarters is 20. So let's go ahead and calculate the overall average. The overall average would be the 200, which is the total sales, divided by the 20 quarters that I have. So 200 divided by 20 gives me 10, which is the 200 divided by 20. This is my overall quarter average. Let's go ahead and compute. Let's go ahead and calculate quarter average. 50 divided by 5 quarters that I have would give me 10. 28 divided by the 5 quarters of quarter 2 that I have gives me 5.6. Similarly, 30 divided by 5 is 6, and 92 divided by 5 is 18.4. So these are my quarter averages, and this is my overall average. To calculate seasonal indexes, you would take the quarter average by the overall average and divide it. So 10 divided by 10 gives me 1. So quarter 1 is average for the year. 5.6 divided by 10 is 0.56. So quarter 2 is at 0.56. If 1 is the base for the year or the average for the year, quarter 2 is about 44% below the average. Sales for quarter 2 are about 44% below the average for the whole year. 6 divided by 10 is 0.6. So if base is 1, quarter 3 sales can be approximated to be about 40% below the average for the year due to seasonality. And quarter 4, 18.4 divided by 10 is 1.84. So quarter 4 is about 84%, sales for it are about 84% above the average. So these are the seasonal indexes, and the way we computed them was by taking the quarter average and dividing it by overall average. Now that we've done this, we need to deseasonalize the data. Why do we need to deseasonalize the data? Let me take you back to this chart here. Notice how the seasonal effects are pronounced, and therefore the data values, the actual values, are so far away from the trend line. If I were to push a trend line or calculate a trend line to go through this, I know my results are not going to be very good. In fact, if you were to take this actual time series, periods 1 through 20, and plug it in POM/QM or plug it in Excel and do a trend analysis for it, the trend equation is going to be, as you can see it here, maybe you cannot see it, I'll write it over again. It says y is equal to negative 0.484 plus 1 times t. And the correlation coefficient for it is 0.72, and the coefficient of determination is only 52%. So that's not a very good, strong model. So we know we have to fit a trend line because we know there is trend in our data. But what if we were to deseasonalize the data, take the effect of the seasons out first, then fit a trend line through the data? If we do that, we're going to get this right here. Look at how small now the variations are of the data around the trend line. But this is deseasonalized data. That has been fit through the trend equation. Let's see how we get that. To deseasonalize our data, what we need to do is take each of these actual values, past data values, and divide them by their respective seasonal index. 1.56, 0.6, and 1.84. So because seasonal index for the first quarter is 1, we know to deseasonalize it, there is no seasonality over and above the rest of the year. So that's very average for the year. So we know the deseasonalized data for quarter 1 are all going to be the same value. So 4, 6, 10, 12, and 18 divided by 1 gives us 4, 6, 10, 12, and 18. This second chart that I'm showing you, table, gives you the deseasonalized data results. It says divide actual by seasonal index to get deseasonalized data. So let's see how we generated the second deseasonalized column. If we take 2 and divide it by 0.56, its seasonal index, and if we take 4, 3, 9, 10, each of them, and divide them by their respective quarter 2 seasonal index, then we will get this column that you see here. And these are deseasonalized data. Now look, quarter 2 has a seasonal index that is 0.56, which is below the year. So we know that that 2 right here is low because of seasonality. If seasonality was not a factor, we would expect that quarter sales to be higher than 2. And in fact, that's what happens when we divide our actual data by our seasonal index and deseasonalize the data, we get that 2 to be somewhat equivalent to 3.6 organs that were sold. So accordingly, you will deseasonalize all of this data. Now, this trend equation, the second one that I showed you right here, which has less variation of the data around the trend line, is actually the deseasonalized data that has been plotted. So if you were to take this deseasonalized time series right here, this is quarter 1, starting quarter 1, all the way to quarter 20, or time value, or past period 20 quarters ago to just 1 quarter ago, because this is all in chronological order. If you were to take this and plug it in POM/QM or in Excel to calculate a trend line, you will get this scatter diagram, this line graph, and you will get this information that I will show you. Now, the y hat is 0.308 plus 0.92t, and R, or correlation coefficient, is 0.93, and R squared is 86%. Wow, a whopping difference. Look at the 52% here versus the 86% here. There is no comparison. And how did we accomplish it? Just by deseasonalizing the data, reducing that variation so that line of best fit going through the data is a better fit. All right, so now we have the deseasonalized trend equation. What we need to do is make our forecasts using this trend equation, this 0.308 plus 0.92 times t. So now we're ready to make our forecasts. Use deseasonalized data to calculate trend equation, which is what we did, and I showed you what that new equation is. And how do we do that? Our y, or our variable to be predicted, is the deseasonalized data, and x is time. Sorry, and x is time. But remember, these trend forecasts, okay, let's go ahead and do our trend equation. Our trend equation for the deseasonalized data values, I told you what that was. So now we can make future forecasts using trend. But remember, these forecasts that we make will only have trend in them. They will not have seasonality in them because the seasonal index, indexes were used to remove seasonality within the data. So let's make our trend forecasts. That's why I call it T21, T22, T23, and T24, to designate that there is only trend in the data. All right, here was my equation. To make a forecast for period quarter one of year 6, if this is time period 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, then this time would be 21, this time would be 22, this time period would be 23, and this time period would be 24. These are not data values. I'm just putting in the time value associated with quarter 1, 2, 3, and 4 of year 6. This is a common mistake that students make to make a forecast for next year or next time period. So the trend for quarter 21 would be 0.308 plus 0.92 times 21. You would not put 1 in here for quarter 1. You would put 21 because quarter 1 of year 6 is time period 21. And you would plug 22 and 23 and 24 for quarter 1, 2, 3, and 4 forecasts of year 6. We have these values right here. But now remember, these trend forecasts are not adjusted for seasonality. Why are they not adjusted? Because remember, we deseasonalize the data. in order to use the trend or to arrive at the trend equation. So we deseasonalized it by what? By a division. Remember, we took the actual value and we divided it by the seasonal index. So we used division to deseasonalize the data. Now we must reverse the process and multiply to re-seasonalize the forecasts that we have made, the trend forecasts. The trend forecasts that we have made. Okay, so let's go ahead and do that. Here's my seasonally adjusted forecasts. My F21, now this is F for forecast, this is full forecast, adjusted for seasonality and trend and everything. How do we compute that? Our forecast for period 21, which is Q1 of year 6, would be trend forecast from that period times, this is a multiplication, times the seasonal index. We divided to deseasonalize, now we multiply to re-seasonalize, to put a little season back into our analysis. So here was my deseasonalized, here is my trend forecast for Q1, multiplied by 1, which is the seasonal index for Q1, and you get 19.63. This one right here would be the 20.55, which is the trend forecast, multiplied by 0.56, which is the seasonal index for Q2, and that would give me 11.51. This one would be, trend forecast was 21.47 multiplied by the seasonal index of 0.6, and you get 12.88. And this last one would be our trend forecast of 22.34 multiplied by seasonal index of 1.84. And remember, this one we expect it to be way higher because of the huge seasonal impact, and that actually happens to be 41.11. So this one you could say, if you wanted to round up to be conservative, or you wanted to round off, that's a business decision. You could say that mathematically speaking, these are your forecasts, but then of course you could round off or adjust these so that it would be more in line with your practice, business practice that you have. Now, having said that, let me show you how POM-QM can be used to do all of this analysis for you in one shot. All that you have to do is go to, and you cannot see this, but I will read it off to you. If you go to forecasting, time series analysis, choose as method multiplicative decomposition. That's toward the bottom of all the list of methods when you scroll. Then use, for number of seasons, choose 4. You choose 4 because in this model, in this case, we had 4 quarters, so those were our 4 seasons. Basis for smoothing, choose average of all data. Average of all data. Not CMA, not centered moving average, but here we did not use centered moving average. Here, to do this analysis manually, we used average of all the data. I'm not going to do all of this for you to highlight it because there are a lot of graphs superimposed on top of each other, but I will tell you what our new equation is. Our equation is, of course, the same as I had before for the deseasonalized data, which is 3.308 plus 0.92t. But look what happens now to my correlation coefficient and coefficient of determination. R becomes 0.97, and look here, R squared is 94%. Now we had here, let me find that, over here, for our deseasonalized data, our R squared was only 86%. And now, after putting the seasonality back into it, and then comparing my old forecasts, and my old actual values to come up with an R squared, you get 94%. So essentially, this is a much better, and this you can't get any better than this, really. Let me just show you one more thing. If you wanted to, you could calculate MAD and MSE and all that using this model. Now, how could we do that? Remember, our actual values were here, 4, 2, 1, 5. So you could do time period 1, 2, 3, 4, 5, 6, 7, 8, all the way through 20. What we have are actual values, Y, actual, and we could do forecasts using this model. Now, how would I make a forecast using this model from past data? My actual time period for time period 1 was 4. My forecast to be made is my forecast for time period 1. If I were to use this model to go back and make forecasts of our past data so that I can come up with measures of accuracy, this is the method I would use. I would say my forecast is my trend forecast multiplied by my seasonal index. So my trend forecast was 0.308 plus 0.92 times 1, because this is time period 1. Then I multiply it by my seasonal index for quarter 1, which is really 1, and then I would have my my forecast. For quarter 2 of year 1, my actual was 2. My forecast for quarter 2, in my old time series data, would be 0.308 plus 0.92 times 2. But that's only my trend forecast. Then I need to adjust it for seasonality, and I would need to multiply that by 0.56. And you would go on and on and on, and you would do that. And these numbers that you calculate would be your forecasts. You have your actuals. The difference between the actual and the forecast would be your error, and then you could either take absolute value of it or square it or calculate a percentage so that you can compute MAD, MSE, MAPE, etc., etc. You will note that if you go through this analysis, for this particular data, because it has seasonality and because it has trend, this process, this multiplicative decomposition, is the best method, and it would generate the least error. And of course, we demonstrated that it also has the highest correlation coefficient and coefficient of determination relative to or compared to any other method that you might use. For example, none of the smoothing methods of moving average, weighted moving average, exponential smoothing, or even just the pure trend analysis would even compete or come close to the accuracy of this model. I hope you have benefited from this session. Thank you.